Okay, so let's just recap really quick. Chapter 11 has all been on chi-squared distributions. 11.1 was on goodness of fit, and that's when um, you have one population, you really have one thing that you're interested in about that population. And 11.2, we talked about 11.2a, we talked about homogeneity, and that's when you have two different populations or two different treatments, and you're trying to see if they result in the same distribution. And then the third one that we're going to be talking about is association or independence. So we're going to be given something about a population, and we want to know if two things are related. And we actually kind of talked about this back in probability a little bit with a formula for independence, but it's very, very similar, but not quite the same. So without further ado, let's go ahead and talk about your hypothesis, because we know we always start with state, and that's with our hypothesis. Now, I would put these on your reference paper or somewhere where you can reference it pretty quickly, because I think that they're kind of confusing. This the second way to say these are the same thing, by the way. You just have to see, does the question ask you for association or independence, and they mean the same thing, but regardless, I think this one's a little bit easier. The two categorical variables are independent of the population, and then they're not independent. But sometimes they're going to ask about association, and it's confusing because in the null, it's saying that there's no association. So by saying no association, that means that knowing the value of one variable doesn't help us to predict the value of the other one, or that they're independent. So that's why no association is the same thing as saying independence, but I think that that can be confusing. So I would definitely put these somewhere where you can reference it, because you definitely want to get your null and your alternative hypothesis correct. And then the alternative would be there is an association. Okay, so again, knowing this one, if you can just know that the null always starts with that they are independent, and then if they are independent, that means no association. Okay, then we're going to talk about your conditions. No surprises here, hopefully. So you've got your random, your 10%, and your large counts. And again, large counts have to be at least 5, and do not round those large counts. Finding large counts, this has not changed from homogeneity. So slightly different from goodness of fit. So goodness of fit, they need to tell you the proportion or how to figure out what the expected counts is. For homogeneity or for association, to find your expected counts, you do your row total times your column total, and then divide that by the total. And again, your degrees of freedom is not going to change. That's your number of rows minus 1 times your number of columns minus 1. How do you find your chi-squared? And your p-value also has not changed. It's the sum of the observed minus the expected squared, and then divide that by the expected. And remember, what goes into creating a chi-squared is you're finding these differences. So the closer your numbers are together, your observed and your expected, the closer your chi-squared is going to be to 0. The smaller your chi-squared value will be. The larger that difference, the farther away you're going to be. And then the smaller your chi-squared, the larger your p-value. The larger your chi-squared, the smaller your p-value. And that comes from knowing that we have a right skewed distribution here. Okay, before we get into our example, just really quick, I'm going to reference the reference paper, or look over here. So for this one, I'm looking at the relationship between two categorical values. This is my association or independence test. So here's the name of the test, just like always. Here's your chi-squared formula with your degrees of freedom, number of columns minus 1 times number of rows minus 1. And then over here, you've got your 3 conditions like always. Okay, so goodness of fit, homogeneity, association. So I have 2 examples. This first one here is going to bring us right through the whole hypothesis test, and then the last one's going to compare the 3 so that you can see the similarities and the differences. So in this one here, I want to know, is there a relationship between gender and relative finger length? Supposedly at some point we looked at a random sample of, I was going to see if I could zoom a little bit here. Oh, there we go. Much better. The two-way table shows the gender of each student in which the finger was longer on his left or his or her left hand. So the index finger, the ring finger, and then do the data. So that's that sentence that says that we should be doing a hypothesis test, provide convincing evidence of an association between gender and relative finger length for the U.S. high school students who filled out the survey. So looking over here, here's my data. So I've got my female and male, and then the total column, and then how many had the index finger that was longer, the ring finger that was longer, and same length. And not a bad idea to look at a graph of this to see if there appears to be an association. You could just graph it in Excel and look at that. Okay, so here's the hypothesis. So state we wish to test the following hypothesis at an alpha equals 0.05. This came up the other day. Someone asked, what do we use as our alpha value? And normally we use 0.05 unless if you were really thinking about the consequences of the errors, because remember, alpha is equal to the probability of a type 1. So if you were to think of a type 1 error, which is when you reject the null when you shouldn't have, so the null would be true. If that has severe consequences, then you may want to lower that alpha level down to 0.01. If type 2 has some severe consequences, you may want to raise the alpha level, because we saw that if you raise alpha, that's raising a type 1. Type 1 errors and type 2 errors are inverses or inversely related. So then your type 2 error would go down. But I don't think in this situation we have any severe consequences to make either one of the errors to say that there's no association between gender and relative finger length. Or there is an association. So I think we can just leave our alpha value at 0.05. I don't think we need to change that. Okay, I'm just trying to make it so we can see it all, but I guess we can't. Okay, so there's that. Plan, we will use a chi-square test for association independence. I already showed you where to find that. Random, we had a random sample of U.S. high school students, 10%. Assume that there's more than 4,520 high school students. Again, I got that by taking the total here, multiplying it by 10. Who completed the survey? And large counts, all expected counts are at least 5. Okay, so you're like, well, are they? We didn't check that yet. So we should probably come over here. I already have a spreadsheet started. I copied and pasted this over here. Now, I showed you guys last time. To find this, we're going to do a formula. So equals expected counts is row total times column total divided by the total. And then I also told you that we want to keep these cell references absolute, not for all of them. So the one can change because I'm going to drag down. So I want that one to change, but I don't want the column total to change, and I don't want the table total to change. So I'm going to put in those dollar signs on either side of the letter, and that will keep that as an absolute reference. So then I can just drag down, and that puts those numbers in for me. Okay, now same thing over here. Row total times column total. And then we're going to divide that by the total for the whole table. And again, that just comes from finding the probability of one thing occurring and then multiplying it by the total. That's what's happening here. So it all comes from probabilities, which you could just figure out. But like I said, if I can make Sheets or Excel work for me, I'm definitely going to do that. So there's that. And then I drag those down. So if you looked at that, all of those values are at least 5. Okay. So then we're going to go back over and we're in the do portion. So to find the do, you sum up all of the observed minus the expected squared and then divided by the expected. Again, list out a couple to show the AP reader or whoever's looking at your exam that you know how to find chi-squared. So there it is. And then we're going to go over to the calculator or Google Sheets. In this case, I think Google Sheets is pretty easy. And I'm going to take these and copy them. Now, remember, when you paste, you have to paste your values only. If you don't do that, you're going to paste formulas, and that's just going to get messy. So there's your values. Now, just for fun, we saw this in class, but if I were to sum that, you should get 452. So that should match the total for the whole thing. So both the observed and the expected should both add to 452. Before I find my chi-squared, I thought it might be interesting to just look at the difference between the observed and the expected. Oops. Because again, this tells you which one of those numbers affects the chi-squared the most. So we have two numbers, that are equally as far apart. That's kind of weird. The one that represents the 82, so female with ring fingers, is very unexpected. And the 152, which is the male with the ring fingers, is also unexpected because those are the farthest numbers away from the mean. And then the ones that are closest are going to be from their predicted value would be the same length, both female and male. So I just found the differences and thought that was kind of interesting. Okay, chi-squared equals parenthesis observed minus expected squared. Divide that by the expected. This one I do not want absolute cell references. I want it to change every time. There we go. And then lastly, to find my chi-squared, I'm going to sum up that column right there, click enter, and there's my chi-squared of 29.02. I already have that in there, so I put 29.0 or 29.02, it doesn't matter. You're gonna then sketch, I can't sketch right here because I'm not in Cami, but anyways, you would sketch your right distribution, your skewed right distribution, and you would put your 29 on there and shade greater than to show everybody that you're shading 29 to 10,000. Degrees of freedom is 2, because if you look up here, the number of rows is 3. 3 minus 1 is 2. The number of columns is 2. 2 minus 1 is 1. 2 times 1 is 2. So that gives me a degrees of freedom of 2. And then those should be labeled as minimum, maximum, and degrees of freedom. It gives me that value right there, which is my p-value. Since p is less than alpha, we reject the null. If p is small, we reject the null. Therefore, we have convincing evidence, because you always go back to talk about the association. If we've rejected the null, then we have convincing evidence that there is an association between gender and relative finger length for U.S. high school students who filled out the census at school survey. Now, a couple of things here. These people were randomly selected from the students, the U.S. high school students that took the survey, which means the results we get apply to the U.S. high school students who filled out the survey, all of them. Okay, and we've assumed that there's more than 4,520 of them. So whatever that population is, that's who these results apply to. Because, yeah, that would be it. Okay. Last thing that I wanted to talk about was which do I use when? Because that could also be a little bit confusing. Even percent at this point. Okay, so when do you use which one? So there is a difference between homogeneity and independence. Pretty much for our level of statistics, whether it's AP or college, it will tell you if you want independence and association, because it will say, is there an association or is there an independence? But I was working with a college stat student, and they had to figure out the difference because it was not as obvious. So here's how you tell the difference. With homogeneity, you have at least 2 different populations or treatments. So if you think back to the previous video, it was babies born before 1980 and babies born after 1993. Okay, so 2 very different populations. I think the one that you're going to do some practice on has to deal with I think it was 2 different groups of people. They're like 2 different classes. So there can't be any mix. So it's 2 different groups. Then you want to see if something is the same for both of those groups. For independence association, you have 1 population. So we had the randomly selected, the people from the U.S. students who completed the survey, 1 population. Then we want to see if their finger length is associated with their gender. So anyways, 1 population, and then you're trying to see if things are related versus more than 1 population. That's kind of the giveaway. Okay, so here's, like I said, the last example. Here's data, and they're trying to see Well, they're giving you this and they're saying, what test do you think that you should use? Okay, so the first one that I can rule out is chi-squared, because when you see chi-squared, you are going to see one column or one row. That's it. Okay, so you're only looking at one thing about that population. So if you remember from the main activity that we did, it was with M&Ms, and we were looking at the color of the M&Ms. So it's one thing about that population of M&Ms. So goodness if it does not work here, because we have a variable of age and a variable of whether they use online social networks or not. Okay, if you wanted to use homogeneity, you would have to choose, we would need more than one population than something about those populations. So we would have to randomly select either people from each one of these 6 age groups and then ask them about their how well, or if they use online social networks or they don't. And then we would be comparing to see if they're the same for each one of the age groups. Or you can randomly select people that use online social networks or they don't, and then ask them their age and see if the age distributions are the same for each one of those. Okay, so you're looking to see if they're the same for 2 different or 6 different samples. Independence. For independence, you would take a random sample from the population, you would ask them their age and if they use social networking, and then you would do a chi-square test for independence to see if their use of online social networking is associated with their age. More than likely with this situation, it is that last one, but it could be homogeneity. We just don't have enough information to decide what they're actually looking for here and how the data was collected. So the data collection piece is going to be key, because you need to know how many different populations you have in order to decide between homogeneity and independence. Okay, so not much change today. 11.2 is very, very similar to 11.2b is very similar to 11.2a as far as how a chi-square test is performed. Use Google Sheets. There's your chi-squared statistic. Your p-value is chi-squared CDF. Remember, it's still right skewed. How you find your observed and your expected. And I would say the biggest difference and the most confusing thing is writing the null and the alternative hypothesis. If you can remember this one down here, then association is not too bad. But I would say the biggest thing that people do is they mix up whether there is an association or there is not, in which hypothesis that goes in. So now it is time to practice 11.2. Have fun.